Okay, the last thing we want to do in the gravitation unit is to very briefly touch on angular momentum again. Now this is a topic that we first looked at back in the rotation unit just a little while ago. And in the rotation unit, in rotational motion unit, we always tried to make parallels to translational motion, okay? The motion you learned at the very beginning of the year. And at the beginning of the year, you guys learned that if there is no net force on an object, then the object does not accelerate. No acceleration. And what that also boils down to is if an object doesn't accelerate, that means its momentum does not change. So there's no acceleration or change in momentum. Now, because we're talking about orbital motion, we're talking about something that is rotating, in a sense, around some fixed point. So when we talk about rotation, we talk about force, but more importantly, we talk about torques. So the parallel is that if there is no net torque on an object, then there is no change in angular momentum. The symbol for that is L, and obviously that is the rotational analog or equivalent of linear momentum. Okay, we can talk about linear momentum, the mass multiplied by the velocity of an object. We can also talk about angular momentum. Okay, so if you have something, an object that is in orbit around some, around some point, such as a planet in an orbit around this star, this picture right down here, then it turns out that if something is in an orbit, there is no torque for that object in orbit. Let me go and show you why. Remember that torque, the equation for calculating a torque is given by R times F times sine of theta, where R is the vector representing, R represents a vector that goes from the axis of rotation, so to speak, out to the object, or out to where the force is being applied, and the force in this case is the force of gravity that keeps the object moving and turning. So in this picture, you would have R going from the star out to A, like this, and then the force on A going back in towards the star. Now those are not parallel, they're anti-parallel to each other, but regardless, they're 180 degrees apart. The sine of 180 is 0. So the conclusion here, since F and R are anti-parallel, the theta is 180 degrees, and therefore the torque is 0 Newton meters. Now that's important because that's the only possible torque that could be on this system. Okay? So what that means is, therefore, there must be no change in momentum. No delta L, in other words. Now recall that's L for a point object, for basically what you can approximate as a single point with some mass, is equal to m times r times v, so L must be conserved. L initial, or L naught, equals L. Okay, so this is just all a really fancy way of saying that the angular momentum of a system does not change for an object that is in orbit around something else. And we can use that to solve for speeds and positions when objects are not moving in circular orbits. That's why we like this. That's why angular momentum is important. In the diagram to the right, a planet with a mass of 5 times 10 to the 23rd kilograms is in a very elliptical orbit around its star. if the planet moves at a speed of 7.3 times 10 to the third meters per second at A, which is a distance of 8 times 10 to the 10th meters away from the center of the star, what would its speed be at B, which is 3 times as far away? So the idea here is we're trying to calculate how fast this planet is moving. However, we don't know we know that the orbit is not circular. So we can't use the idea that FC equals FG because that implies a circular orbit, and that's not what we have here. However, what we do have, we know that for any orbit, and this, by the way, this can be applied to circular orbits as well. It's just it's more useful for elliptical orbits because we can't use the circular motion reasoning there. We know that the angular momentum has to be the same at A as it is at B. So we can make a statement that says LA equals LB. And we can clarify that to the mass times the distance away from the star. Sorry, I lost my train of thought. At A times the velocity at A must be equal to the mass times the distance away from the star at B times the velocity at B. Obviously, the star's mass does not change, so we're left with RAVA equals RBVB, and we can plug numbers in for that. We know that the planet is 8 times 10 to the 10th meters away at A, and it's moving with a speed of 7.3 times 10 to the third meters per second. We know that at B, it's 3 times as far away. So I'm just going to write, I'm not even going to figure out what it is. I'm going to write 3 times 8 times 10 to the 10th meters and solve for VB. And you know what? Since we have 8 times 10 to the 10th here and an 8 times 10 to the 10th here, I'm just going to cross those off. I end up just having to do 7.3 times 10 to the third divided by 3. Very simple. VB is 2,433.3 meters per second. So it's essentially what you see happening here is as the distance from the star goes up, the speed goes down. That makes sense. As the potential energy gets higher, the kinetic energy must get lower since energy is conserved in an orbit like this. You're not injecting more energy at any point. So the idea here is that V and R change so that L is constant. Okay? That's a little primer about angular momentum. You might see it, you might not. It comes every once in a while. There's a problem involving angular momentum. It's very easy if you know how to do it. If you don't, then you're kind of lost. Okay? That's all the notes we have about gravitation. Hope you've enjoyed them. I'll see you later.